Hello, I'm Michel Ruiz Robles. The title of my poster is Magneto Fluorescent and Biocompatible Nanocomposites based on magnetic coated with silicon dioxide, cadmium telluride quantum dots, and chitosan for removal of heavy metal ions from water. Here is an introduction. Global expansion of industrial activities have significantly increased environmental contamination due to rapid global expansion. Wastewater, a heavy metal ion non-carrier, originates from different sources including mining, manufacturing, and battery production. These pollutants migrate through waterways, affecting both aquatic and terrestrial ecosystems. Given the detrimental impact of heavy metal ingestions, regulatory bodies such as US EPA and the World Health Organization (WHO) have established permissible limits for these contaminants in drinking water. For instance, the maximum allowable concentrations for lead, cadmium, and lithium are respectively 0.05, 0.003, and 0.004 milligrams per liter, or ppms. To address this critical issue, research has demonstrated that efficacy of chitosans in heavy metal ion removal. In here, we propose the development of magnetic nanocomposites as a potential more efficient and cost-effective purification method. The biocompatibility of these materials is a significant advantage. Furthermore, the incorporation of quantum dots enhances the visibility of a purification process through their high luminescence. This investigation focuses on the synthesis and characterization of magnetic, luminescent, and biocompatible nanocomposites for the removal of heavy metal ions from water. Let's go to the methodology of this study. As shown in here, okay, first, magnetic was synthesized by co-precipitation method on, on aqueous on water. Then we add silica layer coating by Stover processes. After that, quantum dots are added to the nanocomposite using dodecylamine. Last, we coat the nanocomposite, adding the final chitosan layer. Some of the results. Okay. For the results of this study, we characterize the nanocomposite with X-ray diffraction, transmission electron microscopy, as you can see here, UV fluorescence, and atomic absorption spectroscopy. X-ray diffraction. The results of X-ray diffraction show that all material layers are crystalline. Every single addition coating affects directly on the final crystallinity. In here, we could identify diffraction peaks for CDT quantum dots and magnetic cubic phases. And you can see here, with the yellow ones and the black ones. By transmission electron microscopy, okay, we could understand the morphology of the nanocomposite and could also observe and identify the silica and the final chitosan layers. By UVs, at least for the quantum dots, we could observe and know the absorbance peaks for different colors in the quantum dots, as you can see, green, yellow, orange, and red, showing that by fluorescence, for example, the highest luminescence. By fluorescence, we observe the wavelengths of the luminescent peaks, uh, reach the, which reach the maximum for each sample quantum dot peak, and that bare sedentary quantum dot's luminescence decreases as the layer increment of the final nanocomposite, resulting on a reduction, shown here, on a reduction of luminescence of about to 30% of the bare quantum dot's fluorescence. Entity assay, shown in here, was carried out to characterize the viability of the nanocomposites with CACO2 cells known as uh, showing extraordinary viability percentage increase for the complete nanocomposite relative to the nanocomposite where do not add ketosan for the concentration up to 10 micrograms per microliter. And here we justified the usage of ketosans shown here in this green and uh, this pink line is for no ketosan and this green one is for using ketosan in the final nanocomposite. All the nanocomposites show excellent magnetic response, and, and we could be glad if you use the QR barcode uh, here, okay, for watching our nanocomposites in action for a few seconds in YouTube. Talking about the purification of heavy metal ions. By UVBs, we characterize the removal behavior of of the final nanocomposite, the FSDQC, for F is for magnetic, F for silica, D for dodecylamine, Q for quantum dots, and C for ketosan nanocomposites. And it is shown that nanocomposites can remove lead, cadmium, and lithium, with the highest removal percentage for lead, as you can see in this bar, with a plus 92%, and cadmium and lithium with less than 10%, showing that we could potentially in the future add more removal percentage to this too. But for now, lead is the best option to remove for this nanocomposite. By atomic absorption, we could we concluded that our equipment used for this characterization could not detect lead ions due to its lower limit value resolution, shown here like this triangle, meaning that ppm values were lower than the equipment resolution. All our samples given to or used for atomic absorption, uh, all all of them give a reduction, but in a lot of cases, in almost all of the cases, the lower limit of the resolution of the atomic absorption spectrum couldn't be reached. But the ppm values were lower than the equipment resolution, so it's very good for us. Okay, in conclusion, all the results obtained uh, in this poster, right? uh, show that the nanocomposites have the potential to be used in a heavy metal ions removal from water purification protocols in the future, showing high potential, and we could potentially remove all other kind of heavy metal ions. Thank you. Thank you for watching, and I hope to see you at my poster presentation. Thank you.